good morning everybody. So let us start the second part of the module 2, that is anisotropic elasticity. So last class we have covered isotropic elasticity in case of 2D, 3D, or specifically we have tried to derive the different elastic constants when the material behaves within the elastic limit. So, but practically, if we look into that crystal structure of a specific material, due to the orientation of the different atoms at different positions, it actually holds good some amount of anisotropic behavior. So in this case, it is also necessary to analyze the anisotropic elastic behavior of different crystal structures. So this module I will try to cover. First is the anisotropic elasticity for different crystals, and second part will be that orientation dependence of elastic response in case of cubic and non-cubic structure. So if you look into that picture, or from where the anisotropy comes practically. So first thing is that in a single crystal, the elastic properties actually vary depending upon the crystallographic directions. So last class we have discussed these things. If you go back to our last slide, if we see that single crystal structure, and if we measure the Young's modulus along different directions, we found that along the body diagonal the Young's modulus is 273 gigapascal, and along the edge the Young's modulus is 125 gigapascal. So there is a huge difference of this elastic constant in a single crystal of iron. But if we look into that polycrystalline material, since properties may vary within the each grain, but if we consider the aggregate, that means several crystals together, and we can average out all these things, properties. In this case, the properties can be isotropic. But specifically, if the grains are textures, then we can find out that anisotropic properties of the crystals. So in case of polycrystalline, the anisotropy actually caused by the preferred orientation of crystallographic structures. For example, growth direction in the solidified structure that actually behaves, or maybe it is desirable to consider the anisotropic analysis. And second is the lattice rotation during the deformation, that is mostly in case of metal forming process. So these two cases, the anisotropy behavior is most important to analyze. So of course there is a need to discuss Hooke's law also in case anisotropic, like what we discussed in case of isotropic elastic properties. So then it is possible to reduce to perfectly anisotropic to isotropic cases depending upon the analysis of the symmetry exists within the crystal structure itself. So all this material property, i.e. that means some constant term, we can introduce here to analyze the anisotropic behavior of single crystal material. Linear elasticity we have already discussed, where strain is having the linear relationship with the strain, and that relationship can be complied with two different constants. Specifically, that is called compliances and the stiffness. So that constant term actually analogous to the relation between the stress and strain. If we look into that relationship between strain and stress, then we introduce the compliance terms which is typically termed by S. But at the same time, when we relate between stress and strain, in that case we introduce the constant term that is called stiffness. Specifically, if we consider the all possible anisotropic, in this case stress or strain tensor having 9 components. So in this case, this constant term either S or C can be introduced as a matrix form into 9 by 9. So total 81 number of components will come into the picture. But practically to find out all this constant term is really difficult. So we can take the advantage to analyze the symmetric properties of different crystal structure, and it is possible to reduce this huge number of plastic constants term. So let us look into how we can analyze all these anisotropic constant terms. So if we look into in a matrix form, we use the S term, and this is the column vector, that is the strain component. And if we find out that there are normal strain component 3 and other 6 are shear strain component, and right hand side S, so to bring dimensionality, so this column vector is having the dimension 9 by 1. Then we introduce the compliance term S, that should have total dimension 9 by 9, and the stress also is having 9 by 1 elements. So when you try to bring relationship between stress and strain, or components of the stress and strain, we introduce the either depending upon whether stress is right hand side or strain component is the right hand side, we can introduce either S in terms of S, that is called compliance, or in terms of C, that is called stiffness. So in now we will try to analyze that how this can be correlated in case of 3-dimensional state. So in general, 3-dimensional state, we represents the stress or strain component total 6. Looking into the symmetric nature of the stress tensor or strain tensor. So when there is a component of the 6, and then we can introduce that 6 by 6 constant terms, either compliances or stiffness, that means either S or C in this case. Because in case of highly anisotropic material, actually one component of stress can cause strain in all 6 components. So this, it is desirable to bring total 36 constant terms in this case. So stress can be represented in this way and strain can be represented in this way, but in this case stress or strain are having the column vector, strain also having the column vector of 6 components only. So accordingly we can decide the dimension of the column vector or dimension of the matrix. Now if sigma ij equal to sigma ji, that means it's actually produce the symmetric matrix, and the shear strain can be represented in terms of the normal strain component, which is on a specific plane. The transformation factor is considered as a 2e. So in this case, the shear component we can adjust when you are writing the individual component and try to enter within the linear system of the equations, and we can accordingly adjust by looking into whether in terms of shear strain or we are introducing in terms of the normal strain component. Here, that if we look into that symmetric tensor, we represent that sigma 11, then sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, and sigma 33. So in this case, it is having 9 components, but when it is symmetric tensor, then this component and that component remain same. So 1 3, that means sigma 1 2 equal to sigma 2 1. Similarly, sigma 2 3 equal to sigma 3 2. Like that, we can represent the symmetric tensor, but here it is having 6 components. And in case of strain also, we can represent the similar way, that here also it is having the 6 components. Now we represent that the linear system of the equations of the stress and strains in such a way there that epsilon 1 we can represent that sigma 11, sigma 22, sigma 33, sigma 23 in the consecutive way, sigma 31 and sigma 12. So by following these things, so first 3 components are normal stress component, and next it is the shear stress component. So 3 normal stress and 3 shear stress, and accordingly we add or multiply our individual terms by the last compliance system, that by the S term. So in this case we are getting the 6 equations, and with the 6 equations and with the 36 number of 6 by 6, that means 36 number of compliances term. So that 36 compliances tensor are independent and also having distinct terms. So let us look into that things, how we can reduce the compliances terms as well. So in matrix form, the stress strain relation showing that 36 independent components of the stiffness. So like in compliant systems, we can represent the stress strain relation in terms of stiffness also. Instead of writing S, here we can write C11, C12 and this way, and this actually represents the column vector of stress, this actually represents the column vector of strain. But what was in case of in terms of the compliances, we had written strain equal to S into sigma. But here in terms of stress, we are writing the stiffness term, that means C term. So both way we can write this equation either in terms of S or in terms of C, but definitely all these two cases we are having total 36 independent constant term. Now instead of writing stress tensor in terms of 1 1 1 2 2 2 2 3 like that, we can represent or we can follow certain norm or certain notation, and we can simplify the equation in such a way like that 1 1 term can be represented as 1, 2 2 term can be represented 2, 3 3 term as be represented as 3. So that means first 1 1 2 2 3, the 3 normal stress or maybe strain component in terms of the 1 2 3, but shear component maybe in terms of 2 3 1 3 and 1 2, that is 4 5 and 6. So that is corresponding to either shear stress or shear strain. So if we look into this matrix, the notation is like that. First we write 1 1 2 2 3 3. So basically we are moving diagonally with terms of 1, 2, 3, and then terms is like 2, 3, 1, 3 and 1, 2, 4, 5 and 6. So specifically we are following some specific notation first along the diagonal and then back side, and then we found out one specific sequence like this to write the notation in terms of single term, be 1, 2, 3, 4, 5, 6, instead of writing the notation 1, 1, 1, 2, 1, 3 like that. So actually this type of notation is helpful for the analysis, further analysis of this kind of anisotropic problem. So this notation, all this thing is the specifically the simplified version of the representation for the further calculation of this anisotropic cases. Now then, looking into that notation, we can represent the stress component like that: sigma 1, sigma 2, sigma 3, then 4, sigma 4 here, sigma 5 here and sigma 6 here, like this. And due to the symmetric nature of this stress matrix, here it is sigma 6 corresponding to that, and corresponding to it is sigma 5, corresponding to that it is sigma 4. That means that with respect to the diagonal, so both sides is having similar components according to the symmetric nature of this stress. So similarly, of course, when you try to represent the strain matrix, in this case also we are following the similar notation, and we find out epsilon 1, epsilon 2 and epsilon 3, then 4, epsilon 5, epsilon 6, and due to the symmetric nature it is epsilon 6, symmetric nature it is 5 and it is 4. So in this case also we see that we have written that epsilon 6 by 2. So actually that position is for shear component, and if we multiply the shear component, the factor here, then we representing is terms of the normal strain component, and the 2 is because of the factor converting from the shear strain to normal strain. So here also epsilon 5, epsilon 6, epsilon 4 all are the shear component, but in terms of the normal strain component we have introduced within the matrix itself. So this is the typical relation. Epsilon 4 is basically 2 times of epsilon 2, 3, and we can use direct notation gamma 2, 3. Similarly epsilon 5 2 times of epsilon 1, 3, and which is corresponding to the gamma 1, 3, and epsilon 6 is corresponding to the gamma 1, 2. So these all are the shear component we have written. This is the in this way to make the calculation simple calculation. Now, although we observe that there is a symmetric nature of the stress or symmetric nature of the strain, we have considered depending upon the problem itself, but at the same time symmetry in the stiffness or compliances matrix requires that similar kind of relation, that Cij equal to Cji or Sij equal to Sji. So in this case, if we consider the symmetric nature of the compliances matrix or stiffness matrix, then it is possible to reduce the total number of constant terms here. So let us see. So out of 36 components, there are 6 constant terms when I equal to j, specifically I equal to j, that in this case there are 6 components, and remaining 30 components which is related to I not equal to j. But we can find out what is the total number of linear elastic or in case of linear elastic solid, the how many independent elastic constants are there. That is 30 by 5, because 30 was the where I not equal to j, so 50% of that, and where I equal to j, actually I equal to j exists along the diagonal itself. So diagonal element is having total number of 6, and apart from that, either upper or lower triangle part, from there we can find out total 15. So total 20 number of constant terms that are independent constant terms can be possible to bring out when we consider the symmetric nature of the elastic or compliance terms. So in this case, 20 independent elastic constants can be reduced again further by considering the symmetric conditions for the different crystal structure. So we will investigate gradually for the different crystal structure and how we can reduce this total number of constant terms in these types of crystals. But we can say that this total number of elastic constants can also be possible to reduce up to 2, and in case of isotropic properties of the material. So in this case, because isotropic case only there exist 2 number of constant terms. We will subsequently investigate this phenomena, but let us look into that first, how we can bring down the number of constant in case of different crystal structure. So first we need to look into the symmetric nature of the different crystals system. So first system, the symmetric nature we can explain by the axis of rotation. But if you look into one example, that a threefold rotation, for example, threefold rotation is considered as one symmetry if rotation is 120 degree. For example, total 360 degree and threefold rotation 360 divided by 3, that means 120 degree. So after 120 degree of the rotation, the crystal system comes to a position what was at the initial position. So that is the nature of the analysis of the symmetry. So here it is written as threefold rotation. So threefold means if you rotate total 360 degree, so 3 times it can come to the initial position. That means it is having the threefold rotational symmetry. Similarly, different crystal structure or different crystal systems specifically having the different type of symmetric nature. Let us look into that. First is a triclinic. In triclinic, if we know the triclinic, the crystal system, the none of the edge length or lattice parameter are equal with each other, and none of the angles between the edges are not equal with each other. So there doesn't exist any symmetric nature. So center of symmetry doesn't exist actually in case of triclinic. If we look into the next crystal structure, monoclinic, so in this case we can find out the 1-2-fold rotation. So 1-2-fold rotation means, the 2-fold rotation means 360 by 2, that means 180 degree. So with the rotation of 180 degree, the crystals, the arrangement of the atoms also same to the initial structure. So that is the 2-fold rotation in case of monoclinic. Orthorhombic similarly having 2 perpendicular 2-fold rotations. Tetragonal is having 4-fold rotation around 001. So 1 with respect to the specific direction 001, that means 001 generally represents along the axis. So it is having 4-fold rotation. So 4-fold means every 90 degree rotation there is a symmetry exists in this type of crystal system. Tetragonal, okay, rhombohedral also having 3-fold rotation around 111. Hexagonal is having 6-fold rotation around 0001, and cubic is having 4 3-fold rotations around 111. So let us look into that cubic structure. The 4 3-fold rotations around 111. So actually this 111, it represents the direction of the body diagonal. But in case of simple cubic structure, if you look into that, there may be the possibility of the 4 such body diagonals. So that is this represents actually the family of the direction. So this family consists of the 4 different directions, that means 4 different body diagonal in a cubic structure. So that's why it is having 4 numbers of and having 3-fold rotations. 3-fold rotations means it is 360 by 3. So that means every 120 degree rotations with respect to that one body diagonal, then there exists one symmetric nature of cubic crystal system. So looking into all this symmetric nature, we can reduce the total number of plastic constant during the analysis. So first look into that part, that is orthorhombic. Orthorhombic is having 2 perpendicular 2-fold rotations. If we consider this symmetry, then we can represent the C or S, that means compliances or stiffness matrix, like this. So here the constant terms like that 1 1, 1 2, 1 3, 2 2, 3 3, 4 4, 5 5, 6 6. So basically there is 1 2 3 4 5 6 diagonal elements. So that means either compliances or stiffness constant terms, and there are other 2 1 2, 1 3 and 2 3. So that means another 3. So total 9 different constant terms is used to represent the compliances matrix or stiffness matrix in case of orthorhombic crystal system. Similarly, if we try to so before shifting to that, maybe if we look into the structure, the orthorhombic structure, the typical orthorhombic structure is A not equal to B not equal to C, but the angle alpha, beta and gamma, they all are 90 degree. So with this structure we can find out that 2 perpendicular 2-fold rotation, and with this symmetric nature we can find out that this total 9 number of constant terms actually exist in case of the compliances or stiffness matrix for the analysis of orthorhombic crystal structure. Similarly, we can look into the tetragonal crystal structure. Here we find out that A equal to B is typical structure, and that with 2 lattice parameter, maybe this edge and this edge is equal, but that is not equal to C. So maybe this is not equal to that A or B. But alpha, beta, gamma all are 90 degrees. So all the, with respect to the origin, all the edges are 90 degrees. So this type of structure is having 1 4-fold rotations around 0 0 1. So that is 0 0 1 with respect to one axis. So if there exists this type of symmetry, then the stiffness or compliances matrix terms can be represented this way. Say 1 1 1 1. So that means 1 plus 3 3 1 plus 4 4 4 4 1 plus 6 6 1. So this 1 2 3 4, and apart from that there is a 1 2 1 3. So plus 1 plus 1, and this is also 1 3, and that is another one 1 6 1 6 plus 1. So 1 2 3 4 5 6 7. So that means total 7 number of constant terms actually exist in case of tetragonal, or maybe if we analyze the symmetric nature of the tetragonal structure or just tetragonal crystal system. So that find out that, so the message from here is that if we further analyze the symmetric nature of the different crystals, then we can bring down the total number of constant terms. Now if we look into the hexagonal symmetry, that hexagonal crystal structure, I think it is obvious that there exists a 6-fold rotation. 6-fold rotations, that means after around 0001 that direction, that means actually that is corresponding to the C axis. So you know that hexagonal crystal structure is having 4 axis system, that is A1, A2, A3 on the base, and along the Z direction or along the C direction there is another axis. So with respect to that axis there is having 6-fold rotation, that means every 60-degree rotation it brings the symmetry in structure. So with the symmetric nature of the hexagonal structure, so let us look into how many constant terms are there in this case. So 1 1 1 1 here, so 3 3 4 4 4 4, and there is another x. So 1 1 is the one type, 3 is the another type, 4 is another type, and x. If we look into the x, the typical expression of x, see if we look into that S11 and in terms of S12, or in terms of C11 or C12. But in this case, here the 1 2 term is there, so we can bring plus 1 2 term, but 1 3 term also there. That means the x is in terms of 1 1 and 1 2. So we are having total number of constants here 1 2 3 4 5. Because the x is represented in terms of 1 1 or 1 2. So total 5 number of constants is defined in case of hexagonal symmetric structure. And but if you look into that other, but it's a, this is also that compliance or stiffness symmetric also symmetric with respect to that. And if you look into that, the compliances and stiffness term, the factor 2 is used in different way. Actually this factor, whether 2 or inverse of that 1 by 2, that depends on the whether we are using the compliances term or whether we are using the stiffness term here in this case. That means basically it depends on the relationship either with respect to stress strain or just reverse strain in terms of stress. So accordingly this constant term varies. In this case this is to be noticed here. Be very careful with using this compliant. We are representing the equations either in terms of compliances or we are representing the equation in terms of the stiffness matrix. Now we shift to the cubic symmetry structure. So cubic symmetry structure, already mentioned that cubic symmetry, it is having 4 3-fold rotations around 1 1 1. That means that represents the body diagonal. And with respect to the body diagonal, so it is having 4-fold rotations. And if you look into that symmetry, then we find out that S13, maybe in terms of the compliances, S13 equal to S23 equal to S12, similarly S22 equal to S33 equal to S11, and S66, X55 and S44 all are equal. So look into that, we can represent the system of equations like this, epsilon 1 1 in terms of the sigma 1 1. So this is the system of equations, and in this case the compliances or stiffness matrix is represented like this. So 1 1 1 1 1 1, so these all are equal, the diagonal 4 4 4 4 4 4, these all are the equal, and the 1 2 1 2 and 1 2. So basically 1 2 and 3 different elastic constants exist in case of cubic symmetry. So with respect to the symmetric nature of the compliances or stiffness matrix, we can write the linear system of the equations in terms of either strain or in terms of either strain, and if we solve it, Accordingly, we can find out the different constants, or maybe vice versa, the different constants values are available, and we can use the different compliances of stiffness term for a specific problem, and we can correlate with respect to strain or with respect to stress. So thing is that this stiffness matrix or compliances matrix use, and we can convert this in terms of the system of the equations or vice versa as well during the analysis of the different type of crystal structure. So it is obvious that only 3 independent coefficients are bring down in case of cubic symmetry, as compared to 81 coefficients we consider the maximum anisotropy or in case of 4th order tensor. So it is possible to reduce the total number of constant term from 81 to 3 in case of cubic structure when we consider all the symmetric nature of this cubic crystal systems. So if we look into that, the cubic crystal systems is having the 3 different constant terms, S11, S12, S44, or C11, C12 and C44. So in case of cubic symmetry for different material, generally these 3 constant terms is well tabulated form we can get, and we can use from the standard table the values and to solve the different kind of problems. But if you look into that constant term here, the unit of the constant term is basically in terms of the inverse of the Pascal. Let us investigate this thing. Epsilon is basically here the S, or in terms of sigma. So basically the strain is dimensionless quantity, and stress is having the unit of in SI, Pascal or Newton per meter square or this thing. Similarly, to make it dimensionless, that the unit of S is just reverse of the stress unit. That means if this is the unit of stress is Pascal, then S should be to the power inverse. That's why be careful to note it down that S11, S12 and S4, all these constant terms are represented in terms of the inverse of the Pascal, or maybe terapascal. Tera means 10 to the power 12. Here is the standard table for the cubic symmetry or different cubic structure for different materials. The stiffness and compliance terms, different constant terms are represented for cubic crystals. If you look into that in term metal, the aluminium C11, C12 and C44, we can use all these constant terms, or we can use the compliance term S11, S12 and S44. And for aluminium, copper, iron and tungsten, these are the standard values are obtained, but we should be careful looking into these units of this thing. Stiffness constants is the unit of Pascal in this particular table, and compliances in terms by the multiplier 10 to the minus 11, but inverse of the Pascal, and terapascal equal to 10 to the power 12, the multiplying factor Pascal. So to use the numerical value from the standard table, we should be very careful to look into the different units given for the compliance terms and units for the stiffness term. Now, after the cubic symmetry, next stage is that in case of isotropic symmetry, how we can correlate in case of isotropic symmetry, or specifically for isotropic material behavior, how we can use this constant term. So for isotropic materials, and basically we already mentioned that anisotropic for individual single crystal behave anisotropy, or if there exists some texture structure that also behaves in anisotropic nature. But in case of polycrystalline material, when you try to aggregate and randomly oriented grains, that we can consider in an aggregate having the isotropic behavior. So in this case, we represent all these compliances or stiffness terms or that matrix in terms of only two constant terms. So how we represent the compliances of stiffness matrix in case of isotropic behavior? Here we are having C11 and we are having this constant term half of C11 12 minus 12 by 2. So other is the C12. So only having two different constants C11 and C12 to represent the isotropic behavior of the materials here. Now if we look into that, actually C11 minus C12 by 2 equal to C44. These relations actually exist in when the material is the isotropic. But this sometimes this ratio that is called general anisotropy ratio A is this ratio is used to analyze the anisotropic nature of the material. For example, if it is perfectly isotropic, then this relation is true. But it is not perfectly isotropic, then we can introduce this constant term, that ratio. So several metals having the high A value, that represents the anisotropic ratio. So specifically, definitely for anisotropy, A should not be equal to 1. But aluminium and tungstens practically having the values A, actually that ratio, it is very close to 1. So single crystal of tungstens are almost isotropic, that means A is almost equal to 1 in this case. So that ratio actually to represents the anisotropic, but in case of actual isotropic material, this relation holds good. So instead of writing this term, we can write C44 here. So these are the typical compliances or stiffness matrix in case of isotropic material. Now in terms of A's, similar way we can write the compliances matrix in case of isotropic system. So here we just observe that relation between the S44 and S11 and 22, here the multiplying factor is 2, but in case of in terms of the stiffness, the C in terms of the half of that should be carefully noticed. And all these terms, it can be represented by S44 because that is holds good in case of isotropic behavior. So in case of isotropic behavior, though there is we started with the 81 number of components or 81 number of constants in the stiffness or compliances matrix, but we reduced to cubic system up to 3 independents. Then finally in case of isotropic case, we can reduce the constant terms ultimately 2. So now if we have already defined the different elastic properties or different elastic constants in case of, that is for example that Young's modulus, shear modulus and the Poisson's ratio. So that Young's modulus, shear modulus and Poisson's ratio, that can also be represented in terms of this elastic compliances or the stiffness term. So here in terms of compliances, E can be represented 1 by S11 and G is that inverse of 1 by 2 into S11 minus S12, that is equal to 1 by S44, and Poisson's ratio is the S12 by 12. So actually from the standard table available, so using that constant term directly we can evaluate that these 3 different elastic constants, for example Young's modulus, shear modulus and Poisson's ratio can also be obtained. Now if we try to reinvestigate these things in terms of the compliance terms, the epsilon 1, if you go to the linear system of the equations, the epsilon 1 is the S11 sigma 1, S12 sigma 2, S12 sigma 3. So now if you put into the relationship between the elastic constant and the compliances term, then we can find out that S11 was equal to 1 by E, so that we have written, and sigma 1 comes S12 so S12 we can find out that S12 equal to minus S11, that is equal to 1 by E. So basically S12 equal to 1 by nu by E. So if you put that relation, then we can find out this relation, and that is true when we derive in terms of the elastic constants and to correlate in three-dimensional stress state what are the strain or stress relation in terms of the elastic constants E and nu. So in this relation we used only two elastic constants here. Similarly, epsilon 2 can be represented this, or that is actually comes from that relationship of this compliance subsistence term, and similarly epsilon 3 can also be represented like this. So epsilon 4, epsilon 5, epsilon 6 in terms of the S11, S12, or in terms of the S44 we can represent, that is G shear modulus, and in terms of shear modulus epsilon 5 and epsilon 6. So these are the three-dimensional stress state within the elastic limit that different strain component or stress component can be correlated with respect to the elastic constants, but at the same times, if we know the compliance terms or stiffness terms from the analysis of the anisotropic behavior in case of different crystal system. And this constant term can be, to evaluate this thing, this constant term can also be used to estimate the different elastic constant term. So similarly, we can represent in terms of the stiffness that stress related to strain. So all similar way we are representing here. So now in summary or typical practical points when you try to analyze the anisotropic, where it can be applicable in practically. First thing, a great number of materials actually can be treated as isotropic, although they are not microscopically so. So what does it mean? That materials can be treated as isotropic without this, but this isotropic behavior is possible when we are not focusing on the individual single crystal structure, rather we are trying to focus on the specific microstructure, that is also aggregates of the several grains, and then in that case we can use the isotropic behavior, we can analyze the further. But if we individual grains exhibit the crystalline anisotropy, that is definitely true, and symmetry, but when they are form a polycrystalline material or polycrystalline aggregate, and the grains are randomly oriented, then the material can be considered as a isotropic behavior, microscopically isotropic. But if the grains forming the polycrystalline aggregate having some tapered orientation, the material is microscopically anisotropic. So in this case, if there exists some tapered orientation, then we should consider the anisotropic behavior for this specific materials. But often material is not completely isotropic, that is true. If the elastic modulus E is different along three perpendicular directions, basically irrespective of the direction, the elastic modulus are different, the material is orthotropic. So composites are a good example of this type of anisotropic behavior. Now while we apply all this anisotropic for specific situation. For example, a laminated composite have different fiber orientations, so they are the orthotropic. Symmetry with 9 independent elastic constants. So actually this is analogous to the orthorhombic symmetry, and that possesses symmetry about the 3 orthogonal planes. The elastic constants along the axis of 3 planes are different. So this is the one case, laminated composites having some kind of non-symmetric structure, or maybe anisotropic behavior can also be considered in this case. But orthotropic symmetry generally understand, or we observe the rolled sheet or plates before and after the recrystallization. The anisotropy is caused by the specifically crystallographic structure in this specific rolling or process. So we can consider this anisotropic as the orthotropic symmetric behavior in this case. Tetragonal symmetry we observe in the plywood, woven cloth, composites reinforced with the woven cloth, where we can find out the tetragonal symmetry. So accordingly, when we try to the anisotropic behavior, we can introduce the constant sum looking into the tetragonal symmetry of this specific structure. Axial symmetry we observe in case of extruded or drawn wire. So this is the specifically this specific type of metal forming processes. So in principle, it is possible to obtain the elastic modulus from a polycrystal for a weighted average of elastic behavior of all orientation crystals present in the polycrystal. So point is that if we try to produce the aggregate or value of the elastic modulus, sometimes we can introduce the weighted average method considering the elastic modulus of individual directions, or to analyze the in case of different polycrystalline structure. Orientation dependence in the second part. Now we start, that is orientation dependence of cubic crystals, how we can find out the orientation dependence of cubic crystal structure. So specifically one specific direction, the simplest way, what may be the elastic properties in one specific direction, that we analyze in that way. Suppose 3-axis system, we define 1, 2 and 3 other represent 3-axis system, and one we are interested to find out the Young's modulus along the direction, for example along the direction D. So with this configuration, first assume the single tensile stress sigma D is acting along the direction D, and if we find out what is the, so along the direction sigma D is stress is acting, and if we know what is the strain along this direction D, and that ratio can be represents E as the Young's modulus one specific direction at D. So to do that, with this specific configuration, first consider the direction cosines alpha, beta and gamma with respect to the 1, 2 and 3 axis, and the direction cosines is defined with reference to the axis D along the 1, 2 and 3 axis. For example, alpha, beta and gamma is the 3 different direction cosines. So in this case, when you try to analyze the transformation of the stress with respect to one axis to the another axis, if you look into that part, then you can find out the sigma 1, that means stress along one direction 1 simply can be represented by alpha square into sigma D. So that alpha square equal to that direction cosines with respect to axis 1, this is alpha into alpha. Similarly, sigma 2 can also represent beta square into sigma D. So this is the stress component along the axis 2 with reference to the stress direction D. Similarly, sigma 3 can also be treated like that. Now shear component sigma 2 3, so that component 2 3 with reference to the stress along the axis D is simply multiplying by the two direction cosines beta and gamma, sigma 3 1 gamma alpha. Similarly, sigma 1 2 is the alpha beta, all direction cosines we used, and we took the reference stress along the direction D. We can represent the individual component, shear normal component, stress, and the shear component, and along the different axes 1, 2, and 3 axes. Now, for the cubic crystals along the direction 1 0 0, it's any one of the axes. The strain can be represented with the compliances term S11 sigma 11, S12 sigma 22, S12 sigma 33. So that linear relations or that system of equations actually comes from the matrix notation when you using the compliances term in case of cubic crystal structure. Here we see that in that matrix there is a S11, S12 and S12, and other components are 0. So from here we can directly use here, we can find out the relation of the strain and stress in terms of the compliances term. So similarly we can find out the system of equation 2 2, epsilon 2 2, epsilon 3 3, similarly gamma 2 3, 3 1 and 1 2. So here if you see that putting the value of sigma 1 1, or here we can say sigma 1 1 is equal to sigma 1 here. So that is alpha square sigma D. If we put that, then we can find out these three relations. Similarly, the shear component equal to in terms of S44 beta gamma. So point is that we are representing different strain component in terms of the direction cosines with respect to one specific direction D and the stress value along the direction D. So all in terms of the direction cosines and sigma D. Now if we try to resolve the stress, now we need to find out what is the strain component along the direction D. So along the direction D, the strain component can be represented in this, but this actually comes from the transformation of the axis with respect to one axis to another axis. If you look into that formulation, and we can find out that this is the component of the strain along the one specific direction. So this transformation of the stress with respect to one axis to another axis, that will be discussed in the next module, but we use this using that transformation of the strain component with respect to one axis to another axis. Then we can find out the sigma dd in terms of the direction cosines and component along the three different directions 1, 2 and 3, normal strain component as well as the shear component. So from here we can find out that sigma dd, that means strain along D direction, is in terms of the elastic constants S11, S12, S44 and in terms of the direction cosines. But from the direction cosines hold good the relations that alpha square plus beta square plus gamma square equal to 1. If we put it, then we can find out this alpha to the power 4 plus beta to the power 4 plus gamma to the power 4 equal to this relation. And now we put this expression here and we can find out that sigma dt by alpha d in terms of S11 and the direction cosines. Now this sigma actually epsilon dd by sigma d, so strain along direction D, stress along direction D is basically indicates the Young's modulus along the direction D. So that Young's modulus along the direction D is represented in terms of the compliance system S11, S12 and the direction cosines. So further formulation or further analysis of direction cosines in terms of the Miller indices can also be done. Suppose Miller indices of direction D is HKL. So in this case the direction cosines alpha can be represented H by the magnitude root over of H square plus K square plus L square, similarly beta, similarly gamma. So if we put all this expression, we can find out that Young's modulus along direction D is represented by equation 1, where if we know that one specific direction is the Miller indices, so in this case we can find out the Young's modulus with that specific direction using this formula. Now for an isotropic material, if ED is independent of direction, then we can find out that independent of direction if it is only possible if this term is 0, because that HDKL, that term it cannot be never 0. So if this is the 0, then we can find out this relation S44 equal to 2 into S11 minus S12. So that holds good also in case of isotropic material. That we have discussed for the isotropic material, how we can modify from the cubic structures to the isotropic symmetry. We use this we can use this relation to find out or to reduce the further number of constant terms here. So here it is also other way we can find out that this expression, that isotropic material properties hold good in case if this term equal to 0, and that brings the condition S44 equal to twice into S11 minus S12. So all this expression can also be possible to represent in terms of the stiffness constant. Now let us look into investigate this thing, one specific direction. Let us for example 1 0 0 direction. So 1 0 0 direction is basically axis of the cubic crystal. So in this case the direction cosines may be with respect to 1 0 0. So alpha, first direction cosines, so cos 0, that is equal to 1, and but beta and gamma, that actually represents that 0. So similarly in case of 1 1 directions, where the directions cosines alpha, beta, gamma equal to 1 by root 3. So if you try to put the previous formula, then 1 by E, suppose direction D equal to 1 0 0, in this case we can find out 1 by E 1 0 0 equal to S 1 1, because here HKL equal to 1 or upper term equal to actually 0. So 1 by E 1 0 0 is basically S in terms of S11 only. Similarly, if we put D equal to 1 1 1 direction, then we can find out 1 by E T is equal to in terms of the S11, S12 and S44. So that ratio E111 by E100 can also be represented by this. So this ratio actually represents the highest, largest possible anisotropy in cubic crystal. So the orientation dependence of equation 1 can also be expressed in terms of this 1 by D, 1 by E1 in terms of the elastic modulus on the direction, one specific direction, 1 0 0 or 1 1 1 1. So with respect to that we can find out thus this correlation, where F equal to this expression in terms of the direction cosines. So we can use this relation also further to analyze the anisotropic behavior at different directions or this elastic modulus. So similarly in case of cubic material, the shear modular can also be determined in one specific direction or one specific orientation from the elastic constants as well by the application of the following equations. So in this case, the 1 by GD is the shear modulus, and in terms of S44, S11, S12, and these are the direction cosines. So that can also be derived from the one specific direction in case of anisotropic elasticity. Now, if you look into the non-cubic crystals, then specifically for hexagonal crystals, these are the direction dependence of hexagonal crystals in terms of the different constant term S11, S33, S13 and S44, and others are the direction cosines. But if you others means here we use only one direction, cosine gamma, that is the cosine of the angle between the direction t and the c axis. Similarly, for orthorhombic crystals we can use this relation, so direction dependent elastic modulus in terms of the constant term S31, S55, S12, S66, and others are the alpha, beta, gamma are the direction cosines in case of non-cubic crystal, or for example here the orthorhombic crystal. So these are the way to find out the elastic constant terms, Young's modulus or shear modulus. When you are interested to one specific direction, whether it is cubic crystals or whether it is non-cubic crystals, we need to use all this expression for that. So similar way we can explain the anisotropic thermal expansion. So if it is a linear case, then we can find out the strain is one direction, simply what is the coefficient of thermal expansion and the temperature difference. So in this case it is maybe significant when there is a one direction, or if it is there is a existence of the isotropic isotropic properties exist, then we use this relation directly. But if there is a anisotropic behavior also exists in case of, for example, linear coefficient of thermal expansion are different and the different orientation of the crystals, then in general we can analyze the thermal strain by using this formula alpha ij into delta t, so that epsilon ij. So basically in terms of the matrix we are representing the linear coefficient of thermal expansion having all the components. Like stress, we represent what way the stress tensor or the strain tensor. So of course if in this case it is also symmetric tensor, if we consider symmetric tensor, in this case we use the alpha 1 2, alpha 2 1 is the same, alpha 1 3, alpha 3 1 is the same, alpha 2 3, alpha 3 is the same. So this is the symmetric matrix for the linear coefficient of the thermal expansion. It's a similar way we analyze the stress or strain component. So these are the simply notation we used the anisotropic thermal expansion for different cases. So for example, alpha 1 epsilon 11 thermal is equal to alpha 1 delta t, 2 is alpha 2, alpha 3 we use that alpha 4, alpha 5, alpha 6. So for the symmetric matrix we reduced into the 6 components of the thermal expansion coefficient, and where the relation between this alpha 1, alpha 1 1, so this actually relations all bring similar to what we use the notation for the from 1 1 to 1 that we did in case of symmetric stress or symmetric strain. So similar way we can introduce here. So since always the shear component, so we are multiplying by the factor 2 here to that what way we introduce in case of linear strain and normal strain and the thermal shear strain. Similar way we introduce that effect in terms of the expansion of the coefficient. So in case of cubic crystals, these are the relations actually hold for the symmetric nature. For the hexagonal and tetragonal we use these relations, and for orthorhombic crystal we use this relation to analyze the thermal strain. And also of course all this difference in the thermal, first we try to bring the different constant terms using the coefficient of the thermal expansion, that actually tells about the anisotropic nature and the different orientation. But again, by looking into the analysis of the symmetric nature of different crystal structures, we can further reduce this constant term to less number of constant term in case of coefficient of the thermal expansion. So this was all about the theoretical part of the orientation dependence of crystal structure. Now we will try to shift typical examples that will help to understand the theoretical part of this subject, or specifically this module, where we are analyzing the anisotropic and isotropic elasticity. So first look into that. First example, the hydrodynamic compressive stress applied to a material with cubic symmetry. So here we have mentioned that cubic symmetry results in a dilation of 10 to the power minus 5. That means the volumetric strain is here 10 to the power minus 5. The three independent elastic constants of the material are given. See 4. We need to generalize the Hooke's law for the material, and we need to compute the applied hydrostatic stress. So definitely the volumetric strain is the sum of this thing, and since it creates the hydrostatic stress, maybe due to the cubic symmetry implies that epsilon 1 equal to epsilon 2 equal to 1/3 of the volumetric strain here. And then other shear component will be 0 due to the symmetric nature of these things. Now if we apply the Hooke's law here, we can find out sigma I equal to Cij into epsilon j, or similar way we can use the other equation also in terms of the compliances, but here the data are given in terms of the stiffness. That means C11, C12 and C44 is given. So we use this relation, and we can find out the system of the equation is like that: sigma 1 equal to C11 epsilon 1 plus C12 epsilon 2 plus C12 epsilon 3. Now if we put all these constant terms here, and epsilon 1 equal to epsilon 2 equal to epsilon 3, that means the strain component, then we can find out the 4 minus 433 kilopascal. So hydrostatic pressure here is the 433 kilopascal here. So this way we can use that different elastic compliances or stiffness term to solve different kind of problem. Let us look into another problem, that we need to determine the modulus of elasticity for tungstens and iron on specific direction 1, 1, 1, that means along the body diagonal, and 1, 0, 0. So along the axis of the crystals, what conclusion can be drawn about their elastic anisotropy? So here if we see that S11, S12 and S44, these are the standard values are available or with this problem itself. So we need to analyze all this in terms of the compliances, not in terms of the stiffness. First, we assume that there is a direction D here. First two cases, 1, 1, 1, and another direction is 1, 0, 0. Because these two directions we need to find out the elastic constant terms. So if we consider D as 1, 1, 1, so suppose D as 1, 1, 1 this direction, and we have defined that other two directions of the crystal axis systems, the X, Y and Z. So 1x 1, 0, 0, 0, 1, 0 and 0, 0, 1. Now with respect to that we need to find out what is the direction cosines with respect to 1, 1, 1. Here if we try to find out, with respect to 1, 1, 1, the direction cosines alpha, beta and gamma are, we can easily evaluate, because these direction cosines can also be find out that with respect to two different axes between this and that, 1, 0, 0 and 1, 1, 1, we can use that. So we have used H1, K1, L1 is the one direction, and suppose H2, A2, L2 is another direction. So direction cosines can also find out like that, H1, H2 plus K1, K2 plus L1, L2 root over of H1 square, K1 square plus L1 square into H2 square, K2 square plus L2 square. And from here we can find out the direction cosines between the two axes. So these are the way to find out the direction cosines between the two directions, and we can find out these are the values of alpha, beta and gamma, and with respect to 1, 0, 0 axis we can find out, and with respect to if again d equal to 1, 0, 0, that also we can find out, and we need to find out 1, 1, 0 also if necessary. So we find out the standard table of direction cosines with respect to one axis. Now we use that standard formula. For that, how we can find out the Young's modulus for a specific direction, E1 by E111 in terms of S11, S12 and S44. Okay, and if we put all these values and here the term of alpha, beta, gamma, that means direction cosines, if we put it, and we can find out 1 by E11 equal to 0.37 and finally E11 equal to 270 gigapascal. Similarly, for iron, we can find out along the direction 100, it is 125 gigapascal. So if we see the Young's modulus along 111 or along 100 direction, in this case there is a huge difference in the values of the Young's modulus. So specifically that it is very obvious that anisotropic behavior, that means that elastic modulus are not same along two different directions. So it is the elastic modulus is very much orientation dependence in case of structure of iron, but if you look into the investigate for tungsten in a similar way, we can find out E11 equal to 385 gigapascal and E100 equal to 385 gigapascal even. So if you observe that tungstens, you along the direction 111 or along the direction 100, it's almost similar. So then we can conclude that tungsten is basically elastically isotropic while iron is elastically anisotropic. So we should be very careful to whether we need to consider the isotropic or anisotropic behavior for the different types of materials. So this is the proof, or this is the example of the anisotropic or isotropic behavior in case of tungstens and the iron at different orientation. Now we look into that next problem. So now consider the problem of the elastic anisotropy. Determine the largest possible anisotropy ratio for copper. So largest possible anisotropy ratio in case of cubic structure, copper is having probably the FCC structure. So in case of cubic structure, largest possible ratio can be defined that ratio of the E along the direction 111 and with respect to along the direction 100. So that standard formulation theory we have already derived. We use this formula and we can find out the largest anisotropy ratio for copper can also be obtained. Similarly, also compare with the effective Young's modulus along 110, 112 direction. So along 110 and along 112 direction, we need to find out the Young's modulus along 110 direction and along 112 direction by the similar approach, and we can make some comments on the whether there is a anisotropy exists at the different directions. Next problem, we'll try to find out in case of isotropic properties of copper crystal, how many elastic constants or compliances are defined. Estimate the Young's modulus, shear modulus and Poisson's ratio of copper assuming the elastic properties. As we discussed that when you try to estimate the Young's modulus, shear modulus and Poisson's ratio for a specific material, we can directly evaluate the E looking into the relation for the isotropic properties of the materials in terms of the elastic compliances or stiffness term. Then we can directly use this relation and we can find out all these elastic properties in case of specific materials. Now one is very specific problem. for example, from the elastic stiffness for a cubic material, then find the elastic compliances. So in this case, we have the data for the elastic stiffness, but we need to find out the elastic compliances term. So in this case, actually this elastic compliances and elastic stiffness, they actually hold true for a specific relation. That is there are two matrices, actually multiply these things, they actually hold true, bring the unit matrix. So unit unit matrix, so or maybe identity matrix. In this case, the diagonal elements are 1 and other elements are simply 0. So for the cubic material, this is the expression of the matrix S, and for the cubic material, this is the expression of the matrix C, that means stiffness matrix. So when you multiply these things, we brings the identity matrix. So in this case, now we have we have expressed all these components 1 1 1 2 1 2 considering the cubic material, cubic symmetry, and here also 1 1 1 2. So position of all this S and C term is the same. Okay. So now first, if we look into that, so there is we need to evaluate because cubic symmetry, in case of cubic symmetry, the constant terms is required only. There is a 3 constant terms, C11, C12 and C44. So basically, if we try to find out the 3 equations at least, then we can solve it and we can find out all these things. But tactfully, we need to consider this relation like that. So here I is actually basically 1 1 1 1 1 1 and other terms are 0. So from here, if we see, try to solve these equations, then first look into the row 1 and row column 1. So from row 1 to column 1, if we find out S11 and C11 plus S12 C12 plus S12 C12, we are getting this equation equal to 1. Here is the 1 term. Similarly, row 6 and column 6, if you look, S44 C44 equal to 1. So we get 2 equations. Next equation, from row 1 and column 2, we can find out this equation equal to 0. Now by solving these 3 equations straightforward, we can find out the relation between S12 and S11 in terms of C. And once we evaluate S12 and S4, and S4 can also be directly correlated, that S44 equal to 1 by C44. So from this expression, we can find out this relation between S term and the C terms, and putting all these values, we can find out this value. So these values can also be compared with the tabulated values available in the standard literature. So these are the way to find out the either S or C when one is given or not, others are not available. So these are the simple elasticity problem. So maybe it is necessary to mention that a cylindrical steel specimen of diameter 5 mm is subject to a torque equal to 40 Newton meter. Will the specimen undergo plastic deformation? Assume tensile yield stress is 300. So here tensile yield stress is given, but we need to specify whether is there any plastic deformation or not. So we know that when it is subjected to a torque, then maximum shear stress can also be obtained, torque and the radial distance or the optimum outer surface distance, and J equal to polar moment of inertia, which is equal to pi r to the power 4 by 2. So r is actually the radius. So T is given, r is given, and J is also multiplied, and then we can find out in this case the maximum shear stress is obtained at 1.63 gigapascal, putting the numerical values. But shear yield stress can also be said that again the multiplying factor 2 here, so that shear yield stress be half of the what was the tensile yield stress. So tensile yield stress is given, from there we can find out what is the shear yield stress value. Now we can compare with respect to the maximum shear stress. So maximum shear stress 1.63 gigapascal is much more than the 150 megapascal. So we can say that therefore the specimen will go under plastic deformation. So here the message is that we need to know when you are comparing the plastic deformation, if the shear yield stress is given or the tensile yield stress is given, accordingly we have to compare with the results, and then we can take the decision whether there is any plastic deformation or not. Now look into another problem. So in this case we need to find out the strain energy in a low carbon steel sample loaded to the elastic limit of 500 megapascal. Young's modulus of low carbon steel is 210 gigapascal. So here we need to find out the strain energy when the limit is up to 500 megapascal. So within the elastic limit, normally in this case for low carbon steel, within the elastic limit up to O to A, this is the, suppose A is the elastic limit here and O to A follow the linear relation, and in this case that strain energy density, so if we physically estimate, so up to this is the OB is actually amount of the elastic strain, so that area actually represents the energy per unit volume. So that area physically represent energy per unit volume if we use at A. So that actually area of this triangle, suppose OB equal to epsilon and O equal to say stress. So half of strain into sigma, that is the amount of energy per unit volume. Now Young's modulus within the elastic limit, Young's modulus equal to stress by strain. So in terms of strain equal to sigma by E. So if we put it here, sigma by E, so it becomes sigma square by twice E. Now the sigma square is the elastic limit 500. So elastic limit at this point, stress value at this point is given sigma 500 megapascal, and the Young's modulus also given. Then we can find out the kilojoule per meter cube. This is the amount of the energy within the elastic limit. So thanks for your kind attention. So hopefully you have able to understand the theory as well as the practical application of this theory through solving of the numerical different kind of problems, and hopefully you'll be able to get some idea from the analysis of the theory as well as some numerical problems. Okay, thank you very much.